Good evening, everyone. Welcome to week 11 problem solving session of our theory of computation. My name is Bobby Deeprai. I am a PhD scholar in IIT Madras. And so, yeah, what is week 11 about? It is we explore different kind of NP complete languages, right? So, in the previous week 10, we discussed about what NP completeness is, why it is important, and how it helps in addressing the P versus NP question. Now, what we want to do is we want to study these NP complete languages, and we want to use this tool that we call reduction, right? Transforming one problem to another, and we want to use that tool to actually show that there are so many NP complete languages. It's not just things like SAT. In the week 10 ended with showing that SAT, that is satisfiability, okay, or CNF SAT or SAT, and satisfiability is NP complete. But it turns out that so many real life problems, okay, as well, and lots of mathematical problems are actually NP complete. Some of them are, say, vertex cover and click problem, and vertex cover, click, and then we have tree coloring, Hamiltonian cycle, subset sum, all these problems. All these problems are NP complete. And how did we do it? We did it via reductions, right? Transforming one problem to another. So before we move on further into this, okay, I want to discuss the solution to the previous assignment. That is assignment 10. Okay. So here we'll be discussing about 3 or 4 questions from the previous assignment, which were on the tougher side. Okay. So let's start. Here's question 4 of assignment 10. It says, let k sat, okay, for k is a natural number and k is at least 2, be the subset of CNF sat where each of the disjunctive clauses contain exactly k literals. What does that mean? For example, what is CNF? That is what we call the conjunctive normal form. So a formula, okay, is in the conjunctive normal form means that there is an AND gate on top and there are OR gates below. For example, this, and then the first level consists of a single AND gate, the next level consists of OR gates, and the bottom level consists of literals. Okay, what are literals? Literals are either variables itself or their negated counterparts. Okay, a not gate applied on a variable. That's what we can imagine them as. So, for example, this is an example of a 2 CNF because the fan-in of the bottom gates, that is the fan-in of the OR gates, okay, the number of inputs it takes is 2. So what is KCNF? I have an AND gate, I have OR gates feeding into the AND gate, and those OR gates, they have at most k inputs, or in fact I think exactly k inputs in this, exactly k inputs. So that is what they are saying. For example, here they are saying this particular formula is in 4 SAT. Why? Because the top gate is an AND gate, right? And the OR gates, okay, each of these OR gates, how many literals do they take? They take 4 literals. They take 4 literals. So this is an example of a 4 CNF, and therefore asking whether this is satisfiable is the problem 4 SAT. Okay, asking whether any 4 CNF is satisfiable is a problem 4 SAT, and it's the question says, since it has a satisfying assignment, since it has a satisfiable assignment, this is in 4 SAT. Now, what might be the satisfying assignment? Say I assign say this all ones. Okay, 2 3 4 5 I assign all ones. Now this guy will become 0, and this guy will also become 0. I'll just assign x1 and x3 as 1. So this is a satisfying sign, right? So therefore this formula isn't for CNF, it isn't for SAT. Okay. Also, in all the disjunctive clauses, exactly 4 literals are present. Yeah. So therefore it's in 4 SAT. Okay. Question says, let's assume that P is equal to not equal to NP. Okay. Which of the following options are correct? Select all that are correct. Okay. So P is not equal to NP. That's what we are thinking. Okay. Now here's the question. 4 SAT reduces to 5 SAT. Is it true? Question is, and in other ways, so what does reduction mean? Reduction means I can take the instance to the problem and map it in polynomial time, okay, and convert it into another instance and use the second problem solver to solve this. For example, if I have a 5 SAT solver, okay, if I have a 5 SAT solver, can I solve an instance of 4 SAT? Okay, if I have A reduces to B means that if I have a B solver, can I efficiently solve A? That is the question. Okay. To show this, what do you need to show? You need to show, okay, that there exists a transformation. Okay, first of all, for all inputs, in sigma star. Okay, and there exists sigma. To take sigma star to sigma star. Okay. And for all input, what happens is I'll not say x. For all sigma, reduce sigma star to sigma star, and I'll not say x. I'll talk about a formula phi. For all phi in okay, for all phi, that's all I'll say. For all phi, for all 4 CNF phi, okay, if phi is in 4 SAT, okay, it is satisfiable if and only if sigma of phi is in 5 SAT. So this is the actual reduction. Okay, this is what we need to show. Okay, we need to show such a sigma, and sigma should be efficiently computable. Okay, so how do I do this? What I can do is, see, phi is a formula, remember, and actually sigma star can be further refined. We can say that sigma star actually maps a 4 CNF and gives a 5 CNF. That is what we want. See, we want the reduction sigma to get a 4 CNF and give a 5 CNF. This is what we want, right? And if 4 CNF is satisfiable, then 5 CNF should also be satisfiable. If the given 4 CNF is not satisfiable, then 5 CNF should also not be satisfiable. That is what you want. Now, say phi is equal to, let's take the same, whatever they take, x1 or x2 bar or x3 or x4, then I think 2 3 4 5, and x2 or x3 or x3 4 or x5. Let's say this is 5. Okay, I want to convert it into 5 CNF so that the satisfiability is same. What I mean by satisfiability same is, if phi is satisfiable, then the new formula that I create, okay, let me call it phi prime. Okay, phi prime should also be satisfiable if phi is satisfiable. So here is the logic. What I do is I pick any literal from a clause. Okay, each of these are called clauses. So each of these or blocks. This is a clause. This is a clause. Okay, and in each of the clause I pick any literal and I duplicate it. Okay, what I mean by that is pick say x1, or let's say pick x4. I duplicate it once. So what I'll do is x1 or x2 bar or x3 or x4 or x4 again. I duplicate it, and x2 or x3 or x4 or x5. Pick any one. Let's choose the last one again. x5. Let's say I duplicate it, or x5. Okay, duplicate any literal. This is what I get. Now what do I observe? Okay, observe that for this formula to be satisfiable, both these clauses must be satisfiable. Similarly, for this formula to be satisfiable, both these clauses must be satisfiable. Okay. Now, if this clause needs to be satisfiable, okay, and let's say this clause is satisfiable, then what happens? This part is satisfiable. Okay. If this clause is satisfiable, then this entire part is satisfiable. Now, if any chunk is satisfiable inside these clauses, since this is an OR gate, since this part is satisfiable, and OR this OR means that, see, either on the left I want satisfiable or on the right I want satisfiable for the entire thing to be satisfiable, right? So since this entire chunk is satisfiable, okay, since this entire chunk is satisfiable, I have this this clause is satisfiable. Since this chunk is satisfiable and therefore this chunk is satisfiable, I have that the whole clause is satisfiable, right? Now since both the clauses are now satisfiable, the entire expression is satisfiable. Okay, and finally, let's say if this is not satisfiable, this is also not satisfiable. Okay, so the entire phi is not satisfiable. Then what happens? Phi prime, okay, this is not satisfiable. If this is not satisfiable, it means that each of after applying the input, each of this is giving zeros. Now, since this extra literal is one of the duplicates, in this case it is x4, it's duplicate of x4. This guy is also 0, because if this was not 0, if this was 1, then x4 should have also been assigned to 1, and this clause would have been satisfiable, right? Similarly, let's assume that this clause is not satisfiable. If this is not satisfiable, then this chunk is not satisfiable, because they are same. If this chunk is not satisfiable, right, then it means each of them evaluated to 0, each of the inputs. And since each of these inputs evaluated to 0, and this is a duplicate of one among one of them, for in this case it is a duplicate of x5, then this will also be 0, and therefore the entire expression evaluates to 0, and therefore the entire phi prime is 0. And what is this? This is a 5CNF. We can clearly see that if phi is satisfiable, if and only if phi prime is satisfied. Okay. So and this phi prime is nothing but the sigma that I talked about, the reduction, right? Satisfiable. This implies that, what was it? 4 sat reduces to 5 sat. This intuitively also, I mean, 5 sat sounds like a more difficult problem, right, compared to 4 sat, because there are 5 literals, and therefore you have this. Let's continue. 6 sat reduces to 3 sat. Now, is this true? 6 sat reduces to 3 sat. Okay, is this true? Well, first of all, we observe that 6 sat is an NP. Why? Because I can give you a small certificate, and the certificate for satisfying certificate for the problem of satisfying a 6 CNF, okay, is that I give you the assignment. I give you the assignment, and then you evaluate the circuit, and then say, oh, okay, this is a satisfying assignment. This is a valid certificate. So efficiently, I can verify is an NP. So certificate is nothing but the satisfying assignment. Okay. So yeah, this is 6 sat. This is an NP. Now we know, what do we know? 3 sat is NP complete. So what if 3 sat is NP complete? If 3 sat is NP complete, then all languages will reduce to 3 sat. All languages in NP will reduce to 3 sat. For all L in NP, the language reduces to 3 sat. Which implies, since 6 sat is an NP, 6 sat reduces to 3 sat. Now, this means this is true. Now, 7 sat reduces to 2 sat. Question is, 7 sat reduces to 3 sat. That is the question. Now, as before, 7 sat is in NP. So 7 sat reduces to, oh sorry, not 3 sat. The question says 2 sat. 7 sat reduces to 3 sat. Okay. And okay. Yeah, so here what we have. So this is slightly different. Okay. Now, as part A, okay, I can use the duplicating. By duplicating, oh yeah. By duplicating, 3 sat reduces to 7 sat. What is the logic here? Like here we use the logic of duplicating. We pick any literal. Okay. The idea is, that is, pick any literal in a clause. Okay. Duplicate it. How many times? If there are 3, I want to convert it to 7, I want to duplicate it 4 times. So that it becomes a 7 sat instance. 4 times. So this means that, like we showed 4 sat reduces to 5 sat, we can show that 3 sat reduces to 7 sat. Now what do you have? This is NP complete. If 3 sat is NP complete and it reduces to 7 sat, this means that 7 sat is NP complete. Right. But what do you have? But 2 sat is in P. It can be solved in polynomial time. That's what we saw in the lectures, right? 2 sat can be solved in polynomial time. We had this implication graph. We constructed using an implication graph that 2 sat is possible. So therefore, thus it would mean that 7 sat reduces to 2 sat would imply that 7 sat is actually in P. Okay. Now, if 7 sat is in P and 7 sat is NP complete, what does that mean? This would mean that if I show that an NP complete language is in P, it means that all the difficult languages in NP reduce to a polynomial time language, right? P language. So this means that P is equal to NP, which is a contradiction. Because the question says assuming P is not equal to NP. So this is a contradiction. This kind of thing is not possible. Okay. Finally, 2 sat reduces to 8 sat. Now, by duplicating any literal in 2 CNF in each clause, how many times? There are 2. In the 2 CNF, there are 2. Now, I want to increase to 8. So, I need to duplicate 1, 2, 3, 4, 5, 6 many times. Right? 6 times. We get a 8 CNF. Right? And like we argued before, okay, and like we argued before, 2 sat reduces to 8 sat. Therefore, this is true. Oh, hi, Akshay. You can hear me?
Yes, sir.
Oh, okay. Okay. So I'll just quickly go over this question once again. Okay. So, but it's rather long, so I'll do it in a short form. Okay. Remember KCNFs. Okay. What is a 3CNF? Okay. What is a CNF? Conjunctive normal form is of this form: AND gate on top and OR gates on bottom. Okay. For example, here, so we are doing OR first. These are the bottom gates. Okay, we are doing OR first, and then AND gate on top. Okay, and a KCNF means that the OR gate, the number of inputs to the OR gate, okay, is K. For example, here, this can be represented by a single OR gate: x1, x2 bar, x3, x4 bar, feeding to a single OR gate. This can be shown as that, and that OR gate feeds to an AND gate, and this feeds, and so on. So, how many literals are there? 4. So, therefore, this is a 4 CNF. And the problem of whether this is satisfiable or not is what is called a 4 sat. And this guy is in 4 sat because it is possible to satisfy this circuit. How? I assign x2, x3, x4, x5 all to 1s. Okay. And then I assign x1 as 1. Okay, x3 is already assigned 1. So whatever I assign the others, it does not matter. So this person will always evaluate to 1. And these are all 1s. So this will trivially evaluate to 1. And the AND of that will give 1. So anyway, it has a satisfiable assignment. And this is a 4th CNF. Okay. So now the question says, if P is not equal to NP, which of the following options are correct? Okay. So it says 4 sat reduces to 5 sat. Let's see. So what is meant by 4 sat reduces to 5 sat? It means I can transform an input to 4 sat to an input to a 5 sat, so that satisfying the input to 4 sat is enough to satisfy input for 5 sat. In other words, I have a sigma. Okay, this is what the actual reduction is, which is efficiently computable. And give me any 4 CNF, give me any input to 4 sat, give me any 4 CNF. If that 4 CNF is satisfiable, okay, then definitely definitely sigma of phi, okay, this transformation, okay, I get a new circuit, that is also satisfiable. And since it is an input to a 5 sat instance, it means it is a 5 CNF. So sigma takes a 4 CNF and converts it to a 5 CNF. Okay, and the other way around also. So a sigma of phi is satisfiable, then phi of 4 satis, phi is satisfiable. Okay, it needs to go both ways. So what is the idea here? Okay, the idea is simple. See, if you have a satisfiable 4 CNF, I want to convert it to a satisfiable 5 CNF. And if you have a CNF that is not satisfiable, 4 CNF that is not satisfiable, I want to convert it to a 5 CNF that is not satisfiable. What I'll do is, we'll take this example of the same formula given here. Okay, this guy. This is satisfiable, means that the first clause is also satisfiable, the second clause is also satisfiable. Okay, right? Because this is an AND gate here. So both of them need to be satisfiable. Okay. What I'll do is, I will simply pick any literal here. I can pick x1, x2 bar, x3, whatever. In this case, I'm picking x4, okay, the last literal in the clause, and I'll duplicate it. I'll write it 2 times, x4 or x4. I've duplicated it. Now, how many literals do I have in my clause? 5, because I've duplicated one of them. Initially there was 4, now I have 5. Good. The next clause, what I do the same thing. I pick any of them. In this case, I'm picking x5. I duplicate x5. So how many were there? 4 each. I've converted into 5 each. So I've got a 5 CNF. Okay, we are already close. From a 4 CNF, I have got a 5 CNF. Now my argument is that if phi is satisfied, if phi is satisfiable, then phi prime is satisfiable. The other way around also, if phi prime is satisfiable, then phi is satisfiable. Okay. So if phi is satisfiable, both of these needs to be satisfiable because there is an AND. Now if look at this clause, this is satisfiable. Okay, this is satisfiable, means that, and note that this part and this part is identical. Okay, and if this is satisfiable, then this part is also satisfiable, means it evaluates to 1. Okay, now if this part is satisfiable, then this part is also satisfiable, right? And there is an OR gate here. What does it mean that if this is satisfiable and this is satisfiable? It means that I give an assignment where this is satisfiable. I give an assignment where it evaluates to 1. So if this part evaluates to 1, it does not matter what this guy is. But obviously, if I give if this evaluates to 1, obviously this the input to this guy is a 1, right? So okay, sorry, no, that is not always true. Anyway, the point is, it does not matter what this person is, as long as this part is satisfiable, the entire clause will be satisfiable. Similarly, since this guy is satisfiable here and it's same as this part, this clause being satisfiable would imply this clause is satisfiable. It does not matter what this person is because there is an OR gate here. So as long as this part is satisfiable, I'm fine. So it's clearly, if phi is satisfiable, then phi prime is satisfiable. Next, I want to argue the other way around. So I'll just say, if phi is not satisfiable, say this phi is not satisfiable, no matter what assignment I give, I cannot satisfy it. So what does it mean? If it is not satisfiable, then both of them cannot be satisfiable. Oh, sorry. If then at least one of them is not satisfiable, right? Because there is an AND gate. That's why this entire formula was actually outputting a 0. So let's say this is the formula that is not satisfiable. So what do you have in the phi prime, corresponding phi prime? Since this is not satisfiable, this entire thing is not satisfiable. Okay, this thing is not satisfiable. This entire chunk is not satisfiable. Now x4, okay, this duplication what I did needs to be given an input 0. Why? Because if this had an input 1, okay, then this x4, since it's the same thing, would have an input 1. If x4 here also had input 1, then how can it be that this chunk is not satisfiable? Right? So it needs to be that x4 is 0. Similarly, let's say this clause is not satisfiable. This would mean that this chunk is also not satisfiable. Now we argue that x5 also needs to be 0. x5 needs to be 0. Why? Because if x5 was assigned a 1, then this x5 would also be a 1, and therefore this chunk would evaluate a 1, and therefore this would also have evaluated a 1, and therefore this clause would have been satisfiable. But that contradicts our assumption, right? So x5 is also 0, and this chunk is unsatisfiable, so it evaluates to 0. 0 or 0 will give you a 0, and this is also necessarily needs to be 0, and this chunk is 0. So 0 or 0 would give a 0, and the entire 5 prime gives a 0. Okay, so if this is not satisfiable, 5 prime is also not satisfiable by this duplication process. Pick any literal, duplicate. Now, so what does it show? It shows that by the definition of reduction, 4 sat reduces to 5 sat. So 4 sat reduces to 5 sat is true. Second question is 6 sat reduces to 3 sat. Okay. Now, the careful observation is that 3 sat is NP complete. Okay. And 6 sat is in NP. Why 6 sat in NP? And the definition for NP, a problem to be in NP, I just give an efficiently verifiable certificate for that. The certificate I give is the satisfying assignment itself. Okay. I make the claim that 6 sat is definitely satisfiable, and you ask me how. I will give you what I'll give you is the inputs, and you'll just evaluate in polynomial time quickly, and then say, oh, okay, evaluates to a 1, so I can do it. So sorry, it evaluates to a 1, so definitely this certificate works out, and therefore this language is in NP. But if the circuit I claim which is satisfiable is not satisfiable, actually, let's say, I can never provide you a certificate. I can never give you a satisfying assignment. So therefore it's in NP. Now, 3 sat we know is NP complete from the lectures, right? Cook-Levin reduction. 3 sat is in NP complete. Now, since it is NP complete, by the definition of NP completeness, for any languages in NP, the language will reduce to 3 sat. All the languages NP will reduce to 3 sat. What does this mean? Since 6 sat is in NP, 6 sat will also reduce to 3 sat. Okay. So 6 sat reduces to 3 sat. Correct. Now the question says 7 sat reduces to 2 sat. Is it true? 7 sat means each of my OR gates will have fan in, will have 7 literals as inputs. Okay. So is this true? That is the question. Now, yeah. Okay. So okay. Yeah. So we used to do that. Sorry, we saw how that duplicating helps, right? We can actually show by that same duplicating argument. Okay, here what did we do? We picked any clause. Okay, and sorry, for each clause we picked a literal and duplicated it into 2 parts. Okay, to convert a 4 CNF to a 5 CNF. That's what we did. Now what we can show is we can actually convert a 3 CNF to a 7 CNF. But what do we know? 3 sat is NP complete. And if 3 sat is NP complete and reduces to another language in NP, then that other language in NP is actually NP complete. So what do? Again, we do the same thing. We pick any literal in the clause, duplicate it 4 times. Why? 3 sat, each clause will look like this, right? We pick any arbitrary thing and duplicate it how many times? 4 times. Now what is this? This is 7. Initially we had 3. Right? So now by the same argument you can say that we did previously, you can say that okay, if this is if 3CNF is satisfiable, if this part is satisfiable, then the entire part thing is satisfiable, and if this part is unsatisfiable, then the entire clause is unsatisfiable. So 3 sat reduces to 7 sat, and 3 sat is NP complete. If 3 sat is NP complete, then 7 sat becomes NP complete by transitivity. And but we know from the lectures, okay, that 2 sat is NP, and if 7 sat would reduce to 2 sat, it means that an NP complete language is in P. An NP complete language is in P, and if an NP complete language is the hardest kind of NP language is in P, then it would mean that whole P of P is equal to NP, which is a contradiction, because we were assuming that P is not equal to NP. Okay. So this duplicating argument will actually hold here also. Question says, is 2 sat reduced to 8 sat? So given an 8 sat solver, can I solve 2 sat? Okay. What we do is, we use the same duplicating argument. We have an instance of 2 sat. Okay. We have a 2CNF. And okay, literals like this. Okay, let me. So what it looks like actually is like this. And there are 2. Okay. What I'll do is, I'll pick any literal from them. Here I'm again choosing the last and duplicate it. How many times? 1, 2, 3, 4, 5, 6 times. And again I'll duplicate this 1, 2, 3, 4, 5, 6 times. And I'll duplicate this 1, 2, 3, 4, 5, 6 times. Then that feeds into the OR gate. And what do I observe? The fan in is the number of inputs to the bottom OR gates is 8. So this is an 8 CNF. By the same argument, if you can satisfy this part, you can satisfy the entire clause. You satisfy the small part, you can satisfy the entire clause. And if you, and in this guy also, and if you cannot satisfy this part, you cannot satisfy the entire thing because of the duplication. Now therefore you have that 2 sat reduces to 8 sat, and therefore 2 sat reduces to 8 sat is still valid, and this is the answer. Okay. So Akshay, is that clear?
Yes, sir.
Okay. I did a quick recap, but let me know if you want me to repeat anything. Okay. So here's another question. Suppose the following statements regarding languages L1, L2, L3 are true. 3 sat reduces to L1, L2 is in P, L3 is NP complete. Okay. 3 sat reduces to L1, L2 is in P, L3 is NP complete. Which of the following options are true? Select all that are correct. Let's try. Okay. L1 reduces to L3. Okay. L1 reduces to L3. Is it true? What do we know about L1 and L3? First, we know that L1, 3 sat reduces to L1. 3 sat reduces to L1. What does this mean? L1 is NP hard. Remember, it's not NP complete yet. Okay. For L1 to be NP complete, what do we need? We want L1 to be in NP itself. So we want both conditions. Okay. So L is NP complete if first condition is L is in NP and second condition is L is NP hard. What does this mean? For all languages in NP, the language reduces to L. Okay. So both these conditions needs to be satisfied, and L1 is NP hard. It's not complete because condition 1 is not known to be satisfied yet, that it is in NP. Okay. Okay, so that much we know. L1 is NP hard. Next, what are we saying? L3 is NP complete. Yeah, okay. Next, what do you know? Okay. L3 is NP complete. L3 is NP. So, is this enough to say L1 reduces to L3? No, right? Because we want the fact that L1 is in NP. Suppose L1 is in NP, then definitely L1 would have reduced to L3 by definition because L3 is NP complete. But we don't know that. So this is not true. Okay, or at least it is not known to be true. Okay. And next, L1 is NP complete. L1 is NP complete. Again, let's see what we know about L1. Oh, 3SAT reduces to L1. Again, what do you have? L1 is NP hard. But is it NP complete? We don't know. In order for L1 to be NP complete, uh, it needs to be in NP itself. So this we don't know. Okay. Sorry. Okay, this is enough actually. L3 is NP complete. L1 reduces to L3. Oh, okay. No, it's fine. Okay. Next, L3 reduces to L1. L3, which is NP complete, reduces to L1. Is that true? Well, that is true. Why? Because L3 is in NP, right? Because it is NP. L3 is in NP, which means that L3 reduces to L1, 3SAT, because 3SAT itself is NP complete. Okay, and reduces to 3SAT, and 3SAT reduces to L1, but 3SAT reduces to L1. If 3SAT reduces to L1, L3 reduces 3SAT, 3SAT reduces to L1, it means by transitivity, L3 reduces to L1. Okay, this is correct. Now L2 reduces to L1. Is it true? L2 is in P, and L1 is this hard language. Okay, and what does it mean for L2 to be in P? It means L2 is in NP because P is contained in NP. Okay, so L2 is in NP. So if L2 is in NP, what does it mean? If L2 is in NP, it means L2 reduces to 3SAT. Right, because 3SAT is NP complete. Now, if L2 reduces to 3SAT, and 3SAT reduces to L1, we have that L2 also reduces to L1. So, what do we have? L2 reduces to 3SAT, and we have that 3 sat reduces to L1. Okay, L2 reduces to 3 sat, and 3 sat reduces to L1, which means that L2 reduces to L1. So this guy is correct, true. Okay. So any doubts, Akshay?
No, sir.
Okay. 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 Another question from the assignment. So, which of the following is or are in P? Okay, the class P, assuming P is not equal to NP. Select all the correct options. Okay. Firstly, is 2 sat in P? 2 sat is in P. It is there in the lectures. The idea is that you can convert it into uh, into a graph. You can convert it into a graph full of implications, and you can test reachability. You can use BFS or DFS after that. So yeah, you check it in the lectures. So I'm not going deep on this, but by the lectures we know that 2 sat is in and is in P. 3 sat. 3 sat cannot be in P. Why? Because suppose 3 sat is in P. We already know that 3 sat is NP complete. So all the languages reduce to 3 sat. But 3 sat itself is easy to solve. That is, 3 sat itself can be solved in polynomial time. All the languages in NP can be solved in polynomial time, and therefore P is equal to NP. But this is a contradiction because the assumption is that P is not equal to NP. So this is not true. Finally, A, C, F, G, G, W, such that G is a CFG which accepts the string W. Given grammar G and string W, check if G generates W. But this is familiar, right? We did this in the context-free languages section. This is a familiar problem, and this can be solved using CYK algorithm. And how much time does it take? It takes order n cube time. We saw this in the lectures. It takes order n cube time, and which is still polynomial, which means that A CFG is in P. Yeah. So this is true. Now ATM. What is ATM? ATM is given a Turing machine M. Description of a Turing machine M. Okay. Oh, sorry. Not just M. It is given M and a string W also. M is a Turing machine, and M accepts string W. This is ATM. Is it in P? Well, ATM is the membership problem. In fact, It is one of the first problems that we saw, which is undecidable. It cannot ever be that ATM is in P, because that would mean that A is decidable. If I say ATM is in P, this would mean that ATM is decidable. But this is clearly not true, because once something is undecidable, it cannot be decidable. Undecidable itself means that I cannot compute it. Okay, I cannot make it decidable. But all these P and P space, and all these classes that we are talking about, we are talking about all decidable languages. Okay, so this would mean that ATM is decidable, which is not true. So this is false. Here. Maybe there's one more question from the assignment, then we'll move on to this week's content. Okay. Fine, right?
Yes, sir.
Okay, fine. Uh, okay. So the question says now, see, P equals NP is the question that we are trying to solve, right? And we want to explore what would help us in showing that P is equal to NP or P is not equal to NP. Question says, which of the following statements, if true, can help us answer whether P is equal to NP? Okay. Let's look at the first question. 3 sat is NP complete. 3 sat is NP complete is known, right? 3 sat is the first language, one of the first languages we saw, which is NP complete. Known. So it does not make sense that knowing that 3 sat is NP complete would resolve P equals NP, because we already know this and we don't know whether P is equal to NP or not. So this is not true. Now, 4 sat is not in P. Now, by the duplicating argument that we saw before, 3 sat actually reduces to 4 sat, which would mean that 4 sat is NP complete. Actually, we don't even need this, but anyway, okay, 4 sat is NP complete. So if 4 sat is NP complete, and say 4 sat is not in P, and suppose 4 sat is not in P, what would it mean? It would mean that P is not equal to NP, because if P is because say P is equal to NP, okay, let's say P is equal to NP, then all the NP complete languages would actually fall inside P. But this is not the case, right? We are saying 4 sat is not in P, so obviously it would be that P is not equal to NP. Next, C and F sat is in P. Again, C and F sat is what? Given a C and F, is it satisfiable? This is not NP. Sorry, what do we say? This is NP complete. So if an NP complete language is in NP, then this would imply that P is equal to NP. So this helps in resolving that. Okay. Also, like, if 4 sat is not in P would mean that P is not equal to NP. CNF sat is in P would mean P is equal to NP. And finally, 2 sat is NP complete. What is 2 sat? 2 sat is in P. We know that, right? 2 sat is in P and 2 sat is NP complete, which means that an NP complete language is in P. It means all the languages in NP are easy to solve, and therefore P is equal to NP. So this also helps in resolving the doubt of whether P is equal to NP or not. Okay. Uh,
Yes, sir.
okay. Yeah. Okay. Good. So yeah. Okay. This is clear, right? Uh, okay. So now we are going to look at some questions on this week. Okay. On this week's content. Uh, it is based on more NP complete languages. So what did we see in the lectures? What did we see? We saw vertex cover. We saw vertex cover, click, Hamiltonian path, vertex cover, click, Hamiltonian path, 3 coloring, 3 CNF, 3 SAT. Okay, and yeah, anything I missed out? I wrote it in the beginning also. Subset sum. Subset sum. These are all NP complete. No, these are all NP complete. Now we want to answer questions based on them only. So what we observed is that there are actually several NP complete languages. Okay. In fact, I think there's a theorem saying that there are infinitely many NP complete languages. Okay. Um, but yeah, uh, these are some particularly interesting problems that can be seen to be NP complete. Okay. Now, here's the question. Suppose it is proved that P is equal to NP. Okay. Which of the following is true? All languages in P are in NP. All languages in NP are in P. For all A in P, A is NP complete. For all A in P except A equals phi and A equals sigma star, A is NP complete. Okay. So yeah, any guesses? What's the correct option? What are the correct options possibly?
I think ABC is.
ABC.
Yes, sir.
Yeah, good. That's exactly the correct answers. Uh, oh, okay. No, no, that's almost correct. And yeah, A is correct, B is correct, and it is D. Surprisingly, okay. It's not C, but on first glance, it is true to think that okay, C may be the correct answer, but there's just a uh, slight problem there. Okay, so firstly, this is trivially true that all languages, because P is in NP, equal to NP means that P is a subset of NP, and NP is a subset of P. Okay, and therefore everything in P is in NP and everything in NP is in P. Now, for all, now P is equal to NP, and we are saying for all A in P, A is NP complete. Now, I'll argue why this may be true. Okay, why this may be true. Now, if A is in NP, if A is in NP, okay, uh, then A reduces to um, okay, one moment. A is in P. A reduces to uh, some NP complete language. B, so that P is NP complete. Okay, yeah, okay. So if A is in NP, then A will always reduce to an NP complete language. Now, further, what you are saying is B is in P. B is itself in P. So A will trivially reduce to any language in P, because what you can do is um, so let A be a language in NP and B be a language in P, and okay, let me, yeah, A is a bad name, so let me call it C. C is an NP and therefore C reduces to B because B is NP complete. Because B is NP complete. Now, by assumption, P equals NP. If P is equal to NP, then what happens? Then B is in P. Now take any A in P. Okay. A will always polynomial time reduce to any other language. A is in P means it will reduce to any other language. Okay. D, let's say. Okay. And for all D in NP. Why? Because because if I want to solve something in polynomial time, I can ignore whatever D says, and this reduction, what I can just simply say is uh, use the polynomial time Turing machine to solve it itself. Okay, I think we did it in the previous tutorial also, that in polynomial time everything reduces to everything in P itself. What you do is you simply ignore what the solver does. Okay, this D solver does, and you just run in polynomial time the Turing machine that you already had, and therefore it will trivially work out. Okay, but yeah, so what this means is that A reduces to NP. Sorry, A reduces to, okay, sorry, for all, if P equals NP, for all A in NP, A in P, A is NP complete. All the languages are NP complete. Now, I think this is the argument that you had in mind. Okay. Uh, but this is this is true for all cases except for A equals 5 and A equals single star. Okay. Why? Suppose A equals 5. What does it mean? So what does it mean? What is the problem A? The problem A is as follows. Yes, if, okay, input, given an input X, output is yes. Okay, if X is in phi, right, X is in A, that's what you do, right? But A is what? A is phi, and no if X is not in phi. But can any input be inside phi? Can any X be inside phi, the empty set? Empty set is already empty. So for give me any string, you will always say no, it is not in phi. No, it's not in phi, and so on. So this is never encountered. right? And x is not in phi. This is always uncountable, always true. That is, no string is in empty set, right? No object is in the empty set. And similarly, if A is sigma star, then what is the problem? The problem A can be stated as, given an input x, output yes if x is an A, that is sigma star, and no otherwise. Well, any string you give me will always be in sigma star. Any string is a element in sigma star. So this is always true. So what does problem A look like? So problem A equals phi will look like, given an input x, output yes. No, output no, always. And when A equals the problem, decision problem, when A equals sigma star is given an input, output yes always. Okay. Now we know both phi and sigma star is in P. Both, because why? Because they are regular both. Okay. Example, yeah, they are regular. Now, okay, now uh, what is the problem? We are saying they cannot be NP complete, even if P is equal to NP. If P equals NP. So what is the problem if say A equals phi or A equals sigma star is NP complete? We are saying it's not possible, right? Why? Why is it not possible? Here is the answer. Because if suppose A equals sigma star is NP complete, then for all L in P, L reduces to A, that is sigma star. But what does reduces to sigma star mean? It means given any x and L, I mean there is a sigma, such that given any x and L, if and only if sigma of x is sigma star. But this is always true. What would that mean? This means that given any x, that is always nil. But for example, I give you satisfiability. Let's say L is satisfiability. I can always give you some kind of circuit, some kind of formula which is not satisfiable. But according to this reduction, it means that since this is always true, it means this is always true. Given any string, it is always contained in the language L. In other words, I want this yes instance maps to yes instance, and no instance maps to no instance. Yes if and only if yes, no if and only if no. But since this side is always yes, this side would always be yes. So given in any language in NP, take it satisfiability or Hamiltonian path or anything, what we are saying is that give me any graph, it will always have an Hamiltonian path. Give me any circuit, it will always be satisfiable. And give me any graph, it is always three colorable, and so on and so forth. So it can never be that sigma star is NP complete. Because if it is NP complete, then you have a triviality on the other side, which is clearly disprovable. Okay. Similarly, for the case of phi, if A is equal to phi, then the answer is always no. It is not contained. No string is contained in phi. But if there is a reduction to this, if some L reduces to phi, the answer for L will also be no. But this is not possible because we can show instances for which the answer is yes. Okay. Similarly, we can show instances where the answer is no. So that is the answer. So therefore, we have that except A equals phi and A equals sigma star, A is NP complete. So C is wrong. But see, it is easy to make a mistake here because by definition it makes it seem that C is true. Okay, is this clear? Okay.
Yes, sir.
Yeah, right. You get it why phi and sigma star cannot be NP complete, because if they were NP complete, then say if phi was NP complete, then any language in P or NP for that case, because we are assuming P equals NP, any language in P, we would have that uh, answer is always no. Okay, but that cannot happen. Okay, uh, okay. Let's look at another question. Okay, so recall SAT. Okay, recall SAT. SAT is given a formula phi such that phi is satisfied. This is SAT. Now we are talking about the problem double SAT. It consists of all the formulas with at least two satisfying assignment. Or this I can change it so that phi has at least one satisfying assignment. Okay, has at least one satisfying assignment. Now consider the problem double SAT consists of all formulas that has at least two satisfying assignments. The question says show that double SAT is NP complete. Okay. Now what does this mean? To show that double SAT is NP complete, it means if I can solve double SAT easily, I can solve SAT easily. Okay, NP complete, right? One way to show is by reduction, and okay, double SAT is an NP complete. I can show by showing 3 SAT, okay, or SAT reduces to double SAT. Okay, so that is there exists a polynomial time computation sigma, which takes sigma to sigma star, or I'll rather say takes a formula phi and maps it to some phi prime. Okay, converts it to some phi prime such that phi is in SAT means that, okay, sorry, not this. If and only if phi prime is in double SAT. What does this mean? This means that if phi is satisfiable, if and only if phi prime has at least two satisfying assignments. So similarly, if phi is satisfiable, I can rename it as phi has at least one satisfying assignment. So what do I want to do? Given a satisfiable formula, I want to convert it into another formula that has at least two satisfying assignments. Okay. Let's focus on the case when there is exactly one satisfying assignment. There is exactly one satisfying assignment for phi. Then phi prime should have at least two satisfying assignments. But if phi has no satisfying assignments, then phi prime should have less than two satisfying assignments. Okay. So let's see how we can do this. Okay. Uh, consider phi. Consider some phi. Take any formula. Okay. Take any formula. Phi. Okay. Oh, okay. Ankit is also here. I'll repeat the question. Okay, Ankit. So the question is: consider the problem double sat. Okay. Double sat consists of all formulas such that phi is a formula with at least two assignments, two satisfying assignments. Okay. Recall that sat is a set of formulas which has at least one satisfying assignment. So we want to show that double sat is NP complete. We want to show that it is NP complete by showing that sat reduces to double sat. Clear? Now, uh, what does it mean by sat reduces to double sat? We want to show that there exists a reduction, okay, which maps phi to phi prime, okay, and such that phi is in sat, okay, phi is in sat. What does phi is in sat mean? That phi has at least one satisfying assignment, if and only if phi prime has at least two satisfying assignments. Okay, so how do you show this? So we begin with by taking any formula phi and assume it's satisfiable. Take any formula phi and say phi is satisfiable. Okay, or say that phi has a satisfying assignment. Okay, and say phi is on inputs x1, x2, and so on till xn. Okay, and it has a satisfying assignment which is x1 is set to a1, x2 is set to a2, and so on. Xn is set to an. Okay, and a1 and so on till an are in 0 1. Okay, these are binary bits. Okay, now this is satisfiable. Okay, phi is satisfiable. So, example, let's say I give it a 0 1 1 0 1 and so on, and x1 to xn, and the output of the phi will become 1 for this particular setting of inputs. What I want to do is I want to modify it slightly and create a phi prime so that whenever this phi has one satisfying assignment, example here, I want to yield two satisfying assignments. Okay. Okay. So what I'll do is as follows. Take phi. Okay. Take phi. Now what I want to do is I'll put an OR gate here. Okay. And I'll put an AND gate here and do some business. Okay. Right now I won't reveal what I'll do. But what is the logic here? For this OR gate to be satisfied, for this new circuit to be satisfied, either phi is satisfiable or this is satisfiable, or this part which I'll call it as phi prime I've already used, or B. Okay, or B is satisfiable because it is an OR gate, or both are satisfiable, no problem. Okay, now if phi is guaranteed to be satisfiable and I want this entire circuit to give me two satisfying assignments, what I'll simply do is this x1 till xn, right? I'll define two new variables. Okay, I'll define two new variables, xn and xn plus 1. Such that this guy is satisfiable exactly in two number of ways. Okay, and how do I achieve that? I'll make one of them complement, and that's it. Why? Now, why will this work? Let's look at xn bar xn plus 1. Okay, and xn plus 1. Okay, this is how many satisfying assignments does it have? How many satisfying assignments does it have? It has exactly two satisfying assignments. What are those satisfying assignments? Are either I set the first one to 0 and set the next one to 1, or I set the first one to 1 and the next one to 0. Is this correct? Okay, yeah. So R. Okay, I'll be more specific actually. Are setting x n oh okay, sorry. This will not. Okay, to do that, what I'll do is, okay, I'll remove this negation sign. Xn and xn plus 1. Okay, and let's draw the truth table. Okay, 0 1 1 0 1 1. Can you think of an operation? Okay, can you think of an operation on these bits such that exactly two parts will be 0 and the remaining will be 1? Exactly 2. It could be somewhere here. It could be somewhere. It could be something like this, or it could be something like this. Can you think of something like this? What is the operation for this? What is or exactly this function? What is this function called? That when one of them is 1, then I'll give a 1. Exactly one of them. Yeah. Yeah.
Zor, I guess.
Yeah.
Zor.
XOR. XOR or XOR. Yeah. Right. Correct.
It's
Exactly.
Zor.
So that is what I'll do. I'll make an XOR here. But you might say, okay, but our circuit has only ORs and ANDs, so how do I make XOR? What else? XOR, okay, can be thought of as follows: xn and xn plus 1, or xn plus 1 and xn plus 1 complement. Okay, this is how you write XOR in terms of OR and AND. So this is exactly what we'll do. We'll do OR of ANDs, and here I'll do xn bar xn plus 1, and here I'll do xn plus 1 xn plus 1 bar. That's it. You've created an OR gate. Sorry, XOR gate. Now what do you know? You know that this particular guy has two satisfying assignments, and by assumption, this person has at least one satisfying assignment. Correct. So, and let's say the satisfying assignment for this person is A1 and so until AN. And how do I satisfy this entire circuit? I can choose the A1 to AN from here, which is the satisfying for phi, and then from here I'll choose 0 1. I'll assign this as 0. I'll assign this as 1. So this guy will be 1, and this will output a 1. So A1 to AN. Okay. Oh no. Okay. Sorry. Sorry for confusing. This is xn plus 1, xn plus 2, xn plus 1, xn plus 2, xn plus 1, xn plus 2. I'm defining two new variables. Plus 1, xn plus 2. Okay. Okay. So yeah, now it must be clear. So I'll assign A1 to AN here, and for this guy I can assign a 0 and 1, and then this part will become 1. So and the entire OR will give a 1. This is one particular satisfying assignment for this phi, which I'll call phi prime. Okay. Similarly, next what I'll do is I'll take A1 to AN as a satisfying assignment. Okay, which satisfies this phi. So this branch is set to 1. Next, what I'll do is I will uh, set xn plus 1 and xn plus 2 as 1, 0. If I do that, 1, 0, then this branch will become 1, and then this branch will become 1, and A1 to AN followed by a 1, 0, okay, is going to satisfy both these parts, and therefore the entire circuit will give a 1. So how many satisfying assignments did I create? So A1 to AN, and then what? 0 followed by a 1. This is one satisfying assignment. And A1 to AN followed by 1 followed by 0 is another satisfying assignment. How many did I create? 2. So if there exists at least one satisfying assignment for phi, we found 2 satisfying assignments for phi prime. Now, similarly, if there are more than found at least 2, but if no satisfying assignment, what if I have no satisfying assignment for phi? What if I have no satisfying assignment for phi? Then no matter what I assign to this right hand side and try to make this right hand side 1, I can never hope to make the left hand side 1, right? I can never make this phi circuit 1 because phi does not have a satisfying assignment at all. So this entire circuit is not satisfied. No satisfying assignment for phi, then phi prime is not satisfied, which means it has less than one satisfying assignment, and therefore converting phi to phi prime, okay, and then solving phi prime for double sat, okay, is enough. So therefore sat reduces to double sat. Note that this is doable in polynomial time. Okay, it's just a matter of adding these few gates, constant number of gates. Okay, and this will just take polynomial time to do. Okay, so double sat is also NP complete. So is this clear? Is this clear? Ankit and Akshay.
Yes, sir.
Okay, good.
Yes, sir.
Okay, okay, good. Uh, okay, now here is another question. What's the time? Okay. Yeah. Which of the following are known to be true? Checking if a cycle exists in a graph is NP complete. Checking if a cycle passing through all the vertices in a graph is NP complete. Checking if there is a subgraph of size m isomorphic to Km. What is Km? Km is complete graph on m vertices. Okay. It is a complete graph on m vertices. And next, given a graph G and two vertices S and T, checking if there is a path from S to T is NP complete. So yeah, any guesses on which of these are NP complete? Or at least known to be NP complete? Okay, let's look at the first one. Uh, Checking if a cycle exists in a graph is NP-complete. Is it possible to come up with a simple algorithm for this? How do I check whether a cycle exists in a graph? How do I check whether a cycle exists in a graph? Or in other words, check if it is not a tree or not. Okay. What I'll do is as follows. Pick any vertex.
Sir, if we are able to come to the same vertex after following a path, then we are
Exactly.
able to find out that there is a cycle.
Yeah. After following a path. But how do you know which path to follow?
To be a cycle in a graph, then there should be, if
Then
there are multiple paths, then we need only one path where a cycle is found to check whether
yeah,
there is a cycle
exactly.
or not.
Right. So if there are multiple paths to uh, go to the same, if there are multiple paths to go to the same vertex, let's call it u and v, then there is a cycle, right? But how do you come up with an algorithm to find this? That is true, exactly, and that is close to the algorithm which I'm. There's a simple algorithm for this. How are you going to figure out where the cycle is, or whether there is a cycle or not?
Sir,
Hmm.
there are two graphs, two algorithms, breadth first search and depth first search.
Exactly. What we'll choose is depth first search. Okay.
Yes.
So the idea is, what is depth first search? You have a graph, and you go to the deepest level. Okay, and so on. You keep picking path, and then you keep go to the deepest level. Once you've entered sort of a leaf node, then you start what is called backtracking, and you come out and then go to the deepest one again, then go backtrack, and then explore and so on. You every time you go to the deepest one. The idea is, if I start at any vertex, okay, and then I start doing DFS, okay, I take several, okay, I have this, okay, and I want to check whether there is a cycle or not. Clearly, there is a cycle here, right? And this is a cycle. And what I do is I pick a vertex and start doing a DFS. I go down the road, and then I start to backtrack, and start to backtrack. I come back to whatever I came. So on backtracking, I don't consider it as a cycle. And again, what I'll do is I'll take this path, and then I'll take I'll go here and backtrack and backtrack. But remember, in the original DFS, I maintain like a visited array, and then I'll not visit further if I've already visited. That I'm not going to do. So finally, what I'm going to do is I'm going to visit such a path so that I keep going deeper and deeper, and then I will choose an edge that will actually I'll end up with an edge that will actually come back to where I started without backtracking. And here I've detected a cycle. So I'll slightly modify the BFS algorithm. So how many times do I need to do this? I mean, some of the vertices may not participate in the cycle, right? I need to do this for every vertex in the graph. So there are n vertices. I'll do this DFS business in every vertex, and DFS runs in polynomial time. Maybe I'll have some overhead for it because I'm modifying it, but still this algorithm will work in polynomial time. So this guy is in P. So it is not known that this is an NP complete. That's why, because if this problem was NP complete, then P would be equal to NP. Okay, fine. Now checking if a cycle passing through all vertices in a graph, checking if there exists a cycle passing through all vertices in the graph. Check if there exists a cycle passing through all vertices in G. For example, so what is a cycle? This is the cycle. So there is a special name for this kind of cycle which passes through all the vertices. Any idea?
Hamiltonian, I guess.
Hamiltonian cycle, right? So this is nothing but Hamiltonian cycle. And by lectures, we know that Ham cycle, okay, is NP complete. So this is true. This is not true. Good. Okay. Now next, checking if there is a subgraph of size M isomorphic to Km is NP complete. Given a graph G, I want to check whether there is a smaller set of subgraph which is isomorphic to Km. What is Km? This is a complete graph on M vertices. So what does this look like? This looks like a complete graph. So there are edges among all of them. So actually there's a term for this also. Any idea what the term is?
For what, sir? For what, sir?
Yeah, what is it? Hello, I cannot.
Which term are you asking for? What?
Based on?
What exactly are you asking, sir?
Oh, okay. What is the term for this? The term, okay. Given a graph, there is a subgraph which is a small complete graph. Any term for that small complete graph? That is what the question is asking, right? Given a G, is there a subgraph, a G and an M? Is there a subgraph which is isomorphic to Km, where Km is complete graph on M vertices? Okay, for example, like if consider this graph, this is a graph. Okay, now
Yes, sir.
there is a key 5 sitting inside, complete graph on 5 vertices. This is a subgraph which is a complete graph. What is the do you know what is the name for such a small complete graph sitting inside a graph?
No idea, sir.
Okay, no problem. It is what is called a clique. So these are called cliques. Okay. So now again, so this is, in other words, the question is asking. Is there a clique of size M in G? Now this is okay. Is there a, let me write it in small letters, clique. This is what is called clique. Okay. is there a click of size m, and this is exactly equal to the click problem. And it was shown in the lecture that click is NP complete. Okay, and click is NP complete. In fact, there's a simple reduction that shows that vertex cover can reduce to click, and click can be reduced to something called independent set. And anyway, uh, click is NP complete. It is a well-known problem. Okay, and so it's a well-attacked problem also in complexity theory, and trying to gather click, trying to solve click in a very quick fashion, because click has a very nice property which is called monotone. So even if you add edges to it, it'll still have a click. Anyway, those things are irrelevant right now. So this is exactly the click problem. And by the lectures, we know that click is NP complete. I would ask you to check out the lectures and look at the proof about why click is NP complete. Okay. And finally, we have this question. Given a graph G and two vertices S and T, check if there is a path from S to T is NP complete. Is it NP complete or not? So here is the question. You have a graph. Okay. And one of them is S and the other is T. Is there a path from S to T? And that is the question. Now, this is clearly in NP, because I can give you the path. Okay. But is this in P? Can I have a simple algorithm to solve it? Any idea? For example, here is a path. So what is a simple algorithm to solve this? Whether there exists a path from two given vertices in a graph. Let me repeat. We are given a graph and two vertices S and T. We want to check if there exists a path from S to T. Okay, so, well, actually, this is a simpler problem than the cycle problem. We don't even need to modify the DFS actually much. So this can be done by DFS. What I'll just do is I'll explore. I'll start from S, and then I'll start my DFS traversal. Okay. And then I go down and so on, and I check. And even if the graph is directed, say given the graph is directed, I can use DFS. I can use DFS accordingly, and I go across one path and so on. Then maybe I'll backtrack and so on. But if there is a directed path, definitely I'll travel down that path using DFS, and then definitely I'll be hitting T. And during my DFS traversal, if at any point I reach T, what do I say? I say that okay, T is reachable. So this is possible. And DFS again takes some polynomial time, right? What is the time for DFS? Some order V plus E or something like that, right? So this takes polynomial time on the number of vertices and edges. So this problem, which is actually a popular problem, which is called reach, okay, is in NP. And later on in the next lecture, you will be seeing a most stronger result that not only is it in P, it is actually inside a smaller class. Okay, And this is a very important problem in the realm of space complexity. Like for example, SAT is important for time, right? Reachability is important for space, because reachability exactly captures space related problems in computer science. Okay. But yeah, right now you don't need to know this, but you'll soon encounter it in the week 12 lectures. Okay. So now, okay, but is this clear so far? All these problems? Okay. So this is not NP complete, because that can be solved in P. At least it is not known to be NP complete. Okay. Is it clear? Akshay, Ankit?
Yes, sir.
Yes, sir.
Okay. Now you have very little time left. What is the next question? Okay, I'll just quickly go over this, okay, before 8. So here's another reduction. Okay, this is what is called the independent set problem. Okay, so independent set problem is as follows. And independent set is a set of vertices I contained in V. Okay, it is a set of vertices such that no two vertices are adjacent to each other. Okay, so for example, here. Okay, so what is an independent set here? This and this and this forms an independent set, right? Anything else? No. So if to see a general idea, if this is a graph, an independent set will be like this. It will be a set which has edges to others, okay, but among themselves they do not share any edges. Okay, so you cannot have something like this. This is not possible. So this is an independent set. Now, what is the problem independent set? Given a graph G and integer k, independent set be the problem of determining whether there exists an independent set of size at least k. Okay, is there an independent set of size at least k? So show that independent set is NP complete. This is the question. What we'll do is we'll show a reduction from a popular NP complete problem, a very popular NP complete problem called the vertex cover, which is also called VC. Okay, it was done in the lectures, but I'll recap what vertex cover is. Vertex cover is a set of vertices such that all edges have at least one endpoint in set of vertices S, okay, in S. Okay. For example, if I have a graph a vertex cover would be something like this, this, and this. Why? Because this, okay, look, I'll color it differently. So I'll color this green and I'll color this blue, because this blue guy covers this edge, okay, and the red guy covers this edge and this edge, okay, and green guy covers this edge and this edge and this edge, and okay, there needs to be one more, and the orange guy covers this edge. Orange guy covers this edge and this edge also. So actually a more better vertex cover is if I remove this. So independent set I'm trying to maximize, vertex cover I'm trying to minimize. Okay, I'm always the optimum vertex cover is always which is of smallest size. So what are the application? For example, like I want to find out like what is the, if I want to, let's say Facebook wants to advertise, okay, among uh, different groups of people, and I don't want to give an advertisement to two people who are friends with each other. So vertex cover actually captures exactly that. Since these people are already friends with each other, I'll send the advertisement only to them, or only to this green guy, and in hopes that he will forward the advertisement to these three people. Similarly, I'll send the advertisement to this person so that he'll forward the advertisement to this, and this person will forward the advertisement, and so on. I get a more optimum solution instead of advertising it to everyone. So similarly, Facebook may be interested in finding in within the graph of friendships whether there exists a vertex cover of a certain size or not. Right. So then similarly, yeah, this is a problem. So and VC is known to be NP complete. What we'll quickly show is that vertex cover reduces to independent set. Okay, how does vertex cover reduce to independent set? We'll see. Claim is as follows. Okay. Now I won't be so rigorous. Okay, I'll just say that if S is an independent set, if S is a independent set, then V minus S is a vertex cover. Okay. Let's see why. So I said an independent set looks like something like this, right? This is S, okay? They don't have edges among themselves, but they have edges to others. So something like this may happen, okay? But they don't have edges among themselves. S is an independent set of size K. Okay. What is V minus S? V minus S is the graph, okay? Now what is V minus S? V minus S is a graph obtained by keeping only the other guys, by deleting these vertices. So I'll just keep this, and so on. Okay, and let's say something like this, and this is my graph, and then I'll keep this. So this is something like somewhat what happens, and now if I delete S, okay, this is what I get. Argument is this needs to be a vertex cover. Why? If this is not a vertex cover, okay, or rather if this was not an independent set, it means that there is an edge among them. Okay, there is an edge among them, but if there was an edge among them, it needs to be covered by the vertex cover, right? So this guy needs to have that edge among itself, but those vertices are not present in V minus S itself. So it cannot be that there is an edge here. So it cannot be that S is an independent set. S is not an independent set, and V minus S is a vertex cover. Getting it? So anyway, I'll write it this way. So I'll make it here, no problem. So what is V minus S? V minus S are exactly these vertices. Okay, and let's say this is not an independent set. The original, the original S is not an independent set. Then what do you have? Then at least the vertex cover should at least cover this. To cover this edge, either this should be in the vertex cover or this should be in the vertex cover. But the vertex cover does not have it, right? So therefore, if it is not an independent set, then it is not a vertex. But suppose this is an independent set. Suppose this is an independent set. Then what happens? So this is an independent set. If I remove, if I look at only vertices which belongs to others, then first of all they are all covering every edge among themselves itself, and they are covering all the edges among um, the to the vertices of the independent set. But anyway, they do not need to cover anything here because there are no vertices there itself, right? So therefore, whatever remains must form a vertex cover. All the edges must be covered because there are no edges among the independent set itself. So I'm anyway removing all the vertices that belong to the independent set, and still the vertex cover is covering it. Okay, but I did it in a very quick, hard and fast fashion. So, but it's already 8 o'clock. But let me know if you want me to repeat this. Okay. There was one more question, but we are not going to get the time to do it. So anyway, I even though it was in a quick fashion, I hope you got to uh, get a feel of what the reduction is like. Okay, and okay, it's already 8 o'clock. So let me know if you want to have any questions. Otherwise, we can call it a day.
No.
Okay, okay. So I'll stop the recording.